Morning. So we'll start week 14 lecture. So we have two weeks, uh, 2 more weeks to finish the semester. So we'll okay. So remember that we have a two identification formula uh for computing the ATE tau. So one is the prediction formula, right? So basically, we use the conditional expectation. So this is actually equal to uh, expectation of the potential outcome, right? So, so, so this is what we really want to compute, but we don't observe potential outcome, but we can use this one, right? To estimate the tau, conditional expectation and tau. So another formula is to use the inverse probabilistic weighting method. So basically, this is essentially Hurwitz-Thompson estimation, right? So this Hurwitz-Thompson estimation idea can be used to compute the estimate the tau parameter of interest tau. Okay. So then behind this identification formula, you can see that we have actually different models. So the first model, we can call it outcome regression model, where this is the model for the outcome of Y, given your covariate and and the treatment choice of treatment. Another model, we can call it a PS model, propensity score model, which essentially compute the probability of T equal to 1 or 0 given X. Okay. So we want to combine, so idea is we want to combine the two models to protect, to do some robust, to achieve some robustness against the assumptions on one model using the other model, something like that. So, okay, so the starting point is to consider a prediction estimator. So suppose for now that this is known, Q, so this Q function is known and pi function is known. And then if we know that, then one way is to use the construct of prediction estimator. So this prediction estimator computes the potential expected potential outcome for t equal 1, and it compute the expectation of potential outcome for t equals 0, and compute the difference from the population. So this prediction estimator is called essentially a regression estimator. And now let's try to understand what is the bias. So bias, the definition. So this is suppose this is estimator, right? And then bias is this guy. Expected value of this estimator minus the parameter, right? So that is the definition of bias. Okay, and then we take the expectation of this guy. That means we want to take the expectation of this guy. That means we are taking, so the only thing random is X then, right? So we take the expectation. So this guy is just the expectation of Y1 minus expectation of Y0. And then this guy is just the expectation of this guy, right? So, so then that's what it is. That's bias. Okay. And then, of course, if this is correct, so if it is correct, right? If this is really correct, then this will be 0. and this will be 0, right? So this is 0 when this Q function is correct. Okay, if not, then there's no guarantee that this bias is 0, right? Okay, so that is the kind of observation. We kind of take it for granted, but actually there's some is the result is built on some assumption, and the assumption is that this Q function is correct. So that under that assumption, this is 0. But now the question is, what if they are incorrect, right? So so the bias term is 0 if the outcome regression model in this conditional expectation is correct. So in other words, the prediction estimator can be biased if the outcome regression model is not correct. Okay. Now then, idea is okay. Can we estimate the bias, right? Well, it's hard to, but we don't want to use the outcome model because we kind of assuming that outcome model could be incorrect. So then we cannot really use that, right? To estimate the bias. So then we should use something else. And something else in this case would be the PS model. So right, so this is OR model, this is PS model, and then idea is okay. What if so? This is our space, the total space. So we want to condition on this one, but we now think that this part may be incorrect, right? Then if this is incorrect, then we should use this one as true. So if I assume that this PS estimator, okay. So if assume that this PS estimator, PS model is true, then okay, so what is bias? So let me write down the bias form. Is expectation. So, so expected value of E1 minus, and then plus expected value of E0. Right? If I use this definition, then bias, this is the bias. Minus of the expected value of E1 plus expected value of E0. And then I want to use the second identification formula here, right? I want to use this second identification formula, IPW formula, because now here this is E1, E0, and this is E1, right? So this is our bias. So bias is expected value E1 minus expected value E0. So E0 minus E1. So then that means I can use this identification formula. So that means we can use E1, E0, right? Something like that. So that is basically what's going on here. So I can use that. See here, this is T1. Minus T, divided by 1 minus pi. So this equality is true when PS model is correct, right? If PS model is correct, then I can use this equality. And after that, So this is a bias. Bias itself is a parameter, right? Because it's a bias is a expectation. Expectation is a parameter. So bias itself is a parameter. So you want to estimate it, okay? Estimate it from the sample. But the estimate the parameter itself is an expectation of something. So then estimator corresponding the estimator is just a sample version of expectation, right? So that's why we use this. We just use because this is a population expectation, and all we have to do is just replace this expectation by the sample version, right? Sample mean. I mean the population, finite population mean. Depends on for it. Same thing here, right? So basically, this guy, estimate this guy, and this guy, estimate this guy. Unbiased estimator. So basically what we are saying is that we have an initial estimator, and then we can compute the bias, estimate the bias of that estimator. Okay. So that is actually good news because you have an estimator, and you actually have an estimator of the bias of estimator, right? So then what is the expectation of this guy? Minus zeta. Okay. So then this guy is expectation of zeta hat minus zeta minus expectation of bias set. And then the first part, this is the definition of bias. So that is bias of zeta hat minus expectation of bias set. Oops, right? So that means what? This bias estimator is unbiased to the bias. Okay, so that is indeed 0. So that means what? That means this guy, bias corrected estimator defined by zeta hat minus bias hat zeta hat is always unbiased. Unbiased estimator of zeta. So if you can, so bottom line is if you can estimate the bias, you can always construct the unbiased estimator by subtracting bias estimator from the original estimator. Okay. So that's what we did here. We did here. So you start with the initial estimator and subtract the bias estimated bias of the original estimator. Then you construct this estimator will be bias corrected. I mean unbiased, right? Okay. So that is basically the idea. So that means we have an initial estimator here, and then we have a bias corrected so estimator of the bias, and then you can eventually construct the bias corrected prediction estimator. So prediction estimator minus bias corrected correction to get something, and then which can be written as this. So this part is just algebra, right? We know what it is, right? We know this is here, and we know this one, which is this one, and then combine. Then this is, so actually this guy is this part. This guy is this part minus this. minus bias correction is. Okay, so you may wonder, so this is, so we call it estimator, but we should be careful because this is a known function, right? Based built on build. So it starts with assuming that this is known. Okay, known. This is function of Q. So conditional expectation is known. But in practice, we never know, right? We never know. We need to estimate from the sample. But the assumption that we know is more like, for the motivating the idea, right? It's not really to construct the estimator, but it's to understand what's going on. So, so that means in the statistical literature, this kind of estimator is sometimes called the oracle estimator. So oracle estimator means that we know the true function. So the estimator built on certain function, right? Build estimator is constructed from a certain function, and we usually will have to estimate the functions, but for now, if I know if I knew these functions, then theory can be easily derived. So this kind of estimator, assuming that the functions are known, is sometimes called the oracle estimator. Okay. In some literature, this kind of function is also called noise parameter. But because this is a function, this is sometimes infinite dimensional. So I don't fully understand what's going on, but I believe that some function is nothing but an infinite dimensional vector, something like that. So that in that sense, they call the function serves as a noise parameter is called infinite dimensional noise parameter. Okay, unbiasedness. Okay. Well, what we just did is to derive, right? To motivate this tau hat PBC prediction bias corrected. Okay, so bias corrected prediction estimator. So sometimes in machine learning, they or some other literatures like the faculty name Art in Stanford. So he used this device. Device. So or some even in machine learning, computer science, they call it rectified. But the point is just a bias correction. So yeah, it's like make a new brand, right? From the old idea, for the old idea. That's quite common. So anyway, so what am I doing? Okay, the idea is okay. The idea is okay. What is the property, right? What is the statistical property of this tau hat PBC? So that is the question, and one that is unbiased. But interesting part is that this is actually unbiased in double sense. What that means. So okay, so this is so let's consider this is a tau bar n, which is the finite population estimator. So this is not really an estimator. You can see that this is because it assumes it's built on potential outcome, right? You never really observe the potential outcomes in practice. So this is not really estimator, maybe a quantity, right? Finite population quantity that happen to be unbiased for tau, right? That happen to be unbiased for tau, regardless of the model, right? So when we say this, no heck. When you say when we say this equality, we don't use any model, right? It's just the sample mean is equal to population mean. That's it, right? Which is true, right? You just assume random variable if a random variable has a finite moment, right? Finite first moment, then sample mean will be unbiased for the population mean. That's it. So no model. So then idea is okay. What I'm going to do is that okay, I'm interested in property of this guy. So I'm interested in computing the error, right? Expectation of this guy, but I want to decompose it in such a way that this is easier to handle. So I want to decompose it into two parts. Okay. And then second part is unbiased. Zero is not zero. Unbiased estimator over zero. Right? Unbiased estimator over zero, no matter what. So that means in order for this to be unbiased, right? So we wish to, this is the goal. We should to show that this is unbiased estimator of zero. Okay. So we want to show that. So that means we have only to check this guy, right? This guy. So that's what we are doing. We compute. We want to check, evaluate this form, and then by algebra, just algebra, you can obtain this. Okay, so that is this is just algebra. Okay, now we wanna take the expectation. Then the expectation can come all the way, right? Okay. But we want to take the expectation conditional on x, right? So we don't have to treat x random variable. So we want to just consider expectation conditional on x, and then see what is random, right? So once you conditional on x, then the only thing random is y and t, right? So either y and t are random, but x is fixed. Okay, so then actually you can say that, let me t and y1 and y0 are independent, conditional on x, right? So this is a strong ignorability. So ignorability or NUC, right? Ignorability means this conditional independence. So that means your expectation. So this guy and this guy, right? T and y, potential upon y are independent, conditional on x. So that means your expectation can be applied separately, right? So this is equal to, so this guy is equal to expectation of t given pi x minus 1 given x times expectation of y1 minus q1 qx1 given x. So the product of the expectation can be factorized. Expectation of the product of expectations. That means what? That means, is this equal to 0? Yes, if this assumption is true, right? So this is okay. So that's interesting because this is 0 if PS model is correct. This is 0 if OR is correct. Okay. So these two, so it's a function of two. So it's a product of two terms. Each one can be 0 on the different models, right? But in the union of the two models, one of the two has to be 0, right? So that means the product is 0. It's unbiased. Okay. So that's so that means this is 0. We can do the same thing here, right? We can do the same thing in the second part too. So the conclusion is that unbiasedness holds if this is correct or this is correct. Okay. So two things. The first thing is that in practice you don't know the cube function and pi function, so you may need to estimate it from the sample. And under the assumption that the estimation error is asymptotically negligible, then you can believe that the estimation error does not really affect to the bias. So estimated bias term has zero expectation if the outcome model is correct. Also, the bias corrected prediction is made is unbiased if the protest model is correct. So it is doubly robust. So the doubly robust in the sense that we require one of two models to be correctly specified to achieve unbiased. Actually, in so it's, yeah, so the meaning of doubly robust is now well accepted, but in the early beginning, I also find a similar phenomenon. I called it doubly protected. Park and Kim 2005. But I'm not famous, so I think this term was not really accepted in the literature. But I think right? We want the protection, right? So we have one model and then we protect using another model, something like that. But anyway, so basically we have one interpretation of the W robust estimator, which is the bias correction of the prediction, bias correction of the prediction estimator, right? So here the interpretation is that we have a we start with a prediction estimator, right? Prediction estimator, and this one serves the bias correction. So this is bias corrected protection, right? Bias corrected prediction estimator. So that's one interpretation. So here's another interpretation. Okay, so another interpretation is this. The idea is this. Okay, here's a this is IPW, right? Which is Horowitz-Thompson. So these two IPW estimator. So without this, right? Without this, this is just based on the propensity score, inverse. So inverse propensity score, inverse propensity weighted estimate, IPW. Okay. So that is initial estimator. And then this one is what? Is to unbiased estimator of zero. Unbiased estimator of zero under. What do I mean by that? So what expectation are you talking about? The expectation we are talking. So the when you say expectation, we are thinking of we are using probability score model, right? PS model. So on the PS model. So if I mean the probability Thompson estimator, the IPW estimator also start with a PS model, right? So everything starts with the propensity score model. Okay. So we have basically unbiased estimator of tau under the propensity score model. But it turns out that this becomes a class. What do you mean by that? So class means a family, right? So we don't have a single element because we can choose different B function to create a different estimator. So it's actually a set, right? And the set is actually infinite number of a set because you can choose infinite number, right? Any integrable function. So it's a huge set, right? Okay. And then what's next? Well, we know that this one is unbiased. That means we can use anything, right? We can choose anything and construct any estimator. But then maybe you want to ask yourself which choice is optimal, right, among this class. So that becomes a very interesting mathematical statistics problem. So you have a class and you have a certain criteria and you want to find the optimal one, right? So that is basically the idea. Okay. So another interpretation is that, okay, here you can actually view it as a initial estimator, which is IPW estimator in the beginning. And then you have an augmentation term. What that means, it means mean zero. I mean, zero expectation, to be more accurate. Okay. So zero expectation is 3. And you might wonder why we don't use y. It's a function of x only. Why not use include y too? Well, the problem is that if you include function of x and y, you cannot really compute it from the sample because you don't observe y, right? You don't observe yi. So you only observe. So here you have a t, but you here this guy is a older sample. So augmentation term incorporate observed information from the final calculation. Why it does not affect the expected value? Because the expectation is zero anyway, right? So it doesn't affect the expected value. It can alter the variance. Okay. Now, the result is that, okay, so this estimator, right? You had AIPW, you had one AIPW is unbiased to mu1, and variance is this guy. Okay, let's compute it. So the assumption is strong ignorability, Stuba positive. So these three are standard three assumptions, and then plus one, plus correct PS model. Okay, so we have four assumptions. Classical three plus PS model. Okay, let me write it. So you had IPW, augmented IPW, IPW. Okay, this is the estimator, right? IPW estimator. And then we want to take the expectation. Conditional on Fn. What do you mean by Fn? Just xi, yi1, yi0. So this is finite population quantity. So if you condition on finite population quantity, the only thing random is ti. That means you are taking conditional expectation of xi, yi. Plus same thing, right? Okay. So idea is okay. By missing it, by ignorability, ti condition on xi and y potential outcome doesn't depend on y, right? So then it, and then this guy is equal to this guy, so cancels. Same thing, you cancels. So then this guy becomes zero, and then first, so then that becomes something like, so conditionally unbiased to the final population mean the y1. Okay. So that means W is So that is so after that, we want to compute the variance. And then same thing. No need to. Oops. So this guy is equal to this guy, right? So that means the variance of this guy, the variance of this guy is so that means this guy is equal to 1 over n variance over y1. So that is this part. Okay. And we want to compute the second term. So second term, we need to have another page. So we want to compute the conditional variance of mu1 AIPW given F, right? So that is okay. So the only thing random here is a t about t, right? So the conditional expectation, conditional variance with respect to t. So anyway, so we can write it as 1 over n e1 xi plus 1 over n ti pi xi by 1 minus p1 xi. So that I just rewrite this one as this one, right? So I just write it. And then here's so the conditional variance. So everything is and square variance of ti given xi by xi square. What I did is that because I know that ti is only ti is a random in the conditional variance. Right. So this only this guy is a random variable. And there's no covariance because ti is independent. So then we just write this. And then variance of ti given xi is a pi xi
minus pi xi squared. So that means you can write it as something like this. That is 1 over n expectation over 1 over pi x minus 1 y1 minus p1 x squared.
That is the
Second term. Okay. So that basically proved this result, right? So we just proved this result. Okay. And then what we want is to find optimal one in the sense that minimizing the variance. So unbiasedness of the AIPW estimator holds regardless of choice of B, right? B1. You can see
this is unbiased. Regardless of choice of B1, right? Because B1, the term in the B1 has a zero expectation. So
in terms of expectation, it doesn't make any difference. But the variance,
if you look at, right, so the expectation doesn't depend on B1, but the variance is a function of B1, right? It depends on B1.
then you,
So now all you have to do is to find the minimizer. Minimizer of this.
okay. How to choose it? So we want to, the
one trick is to so I think that this is a kind of before you prove it, you should know the answer. So in other words, you should have developed some intuition, right? So the point is that, okay, to prove this one, you need to, basically the idea is you should have a conjecture. You first have a conjecture and show that it is actually, so my point is, what is the good conjecture? The good conjecture is the optimal B1 star, maybe a conditional expectation, right? Okay, and then all you have to do is to show that if you plug in conditional expectation, then maybe the variance term can be minimized. And the usual trick is do something like this: y1 minus p1 star x plus p1 star x minus p1 x. Okay, you can write it. You can always subtract and add. And then what? Then you have a square term, right? You square it, and then you can expand the square so that you have something like y1, oops, y1 p star x square plus p star x minus p x square plus 2 covariance, right? Product, cross product. Okay. Then what? Then notice that you're taking on expectation. So if you take the expectation,
So expectation of this guy, okay. Basically this expectation can be written as a sum of the expectation of three terms, right? And then you can show that the expectation of this guy, zero expectation, all you have to show is the expectation of this cross product term is zero. And that is true because conditionally, right? If you could take the conditional expectation, if you take the conditional expectation of y1 given x is the equal to this b star. So that is actually equal to zero. Condition. So cross product is zero is equivalent to show that Pythagorean. So inner product is zero, so that you have a Pythagorean theorem result. So that is what's going on here. So we can show that I think I don't have to show all the details, but I want to just show what is the critical part of the proof, and then it's probably better for you guys to check by yourself. That's probably better way of learning. Okay. So I think that's it. Right. Okay. I do have time, so I can prove it. Let me. You had one AIPW, right? Is remember 1 over n variance of what y1 plus 1 over n expectation of 1 over pi x minus 1 y1 minus p1 x square, something like that. And what I just said is you can actually, so you don't have to worry about this part, right? Because this has nothing to do with the b. So let's take a look at this one. So okay, let's call this star. So what I'm saying is you can write it b1 star x, right? Plus b1 star x, b1 x square is equal to plus cross product expectation is zero. So that means this is non-negative, right? And this is the lower bound is equal to zero. So the lower bound is zero, right? When bx is equal to b star x, which is the conditional expectation. So with equality, if bx equal to conditional expectation of y1 given x. So that is
basically the proof.
Okay. So, so now to reflect, we have a two interpretation of the double robust estimator, right? The first interpretation is that we start with the prediction estimator, right? And then develop the bias corrected prediction estimator. That's the first motivation. Second motivation is totally opposite direction. We start with the IPW estimator, right? And then try to improve the efficiency of the IPW estimator by incorporating the augmentation term, and then choose the optimal augmentation term. So that is actually has a different, totally different direction, right? So prediction, first motivation is start with the prediction estimator, and then use PS model to obtain the W robust. Second one is start with the IPW estimator, and then use some outcome regression model to obtain W robust estimator.
Notice that this, this best choice, right? This best choice uses the outcome model.
So optimal estimator uses an outcome model. Oh, okay. So now I'm going to move on to the example.
The linear model, linear potential outcome model. So we have a two linear regression model for y1 and y0. And the error term could be correlated, right, to each other, but that doesn't make any difference. So, and then what we just developed is this kind of estimator, right? So basically, what is Q?
QXT is actually XI, right? X prime beta T essentially, right? And so estimating the Q function corresponds to estimating beta hat, right? Estimating beta T.
So that is actually this. So prediction, right? Prediction plus bias correction, or start with IPW, and then you have augmentation. So it's really a kind of a universal formula, right? You have a prediction throughout the whole population, and then from the sample part, you can compute the residual, right? And then now that you only observe this residual only for t equal 1, then you want to weight them, right? So inflate this amount to correct it properly.
So this kind of estimator is very intuitive and popular. So this is essentially very close to the two-phase regression estimator, if you remember. So it's week 11, right? Week 11 or 12. We studied two-phase regression estimator, right? So in the two-phase sampling estimator, the only difference is that this pi is known, right? Under our control. In the second phase sampling, we choose pi x function and then do the second phase sampling, right? So this is actually the first phase sample, and then this is actually second phase sample with pi x known rather than estimated. So that's the main difference. So it's very connected actually. So that's why survey sampling and causal inference are really sibling cousin. Okay. Now notice that this optimal estimator is true regardless of the choice of beta hat. So this is not unique. This is not unique because you can choose many different beta hat. Okay, as long as beta hat 1 is unbiased. Okay, so as long as you can compute, you can show this relationship under the outcome model. This belongs to the whole. They are all asymptotically equivalent when both models are correct. When both outcome model and this propensity model are correct, both models are correct, then the estimation how to estimate that hat does not make any difference when both models are correct. But now, here's the interesting, now you want to consider when only one model is correct. So rather than considering, because I know that if both models are correct, then this beta hat does not make any difference. So then that's not interesting, right? And that's probably not realistic. You may not believe that both models are correct. So that's a little bit strong, situation. So now more interesting question is, what if only one out of among the two, right? Between the two is correct, only one. So the first thing is easy, actually. If outcome regression model is correct, we know the answer already, right? This is basically GLS. If you have something like x prime v inverse x inverse, something like that, right? So as long as you know the model variance, then you can use the model variance into the variance covariance matrix and compute the GLS. That's easy. So that you cannot really publish paper with this under this model, right? Because this is kind of trivial. So that's not really, we are not going to cover that. So, but the interesting problem could be that what if only, so I'm going to construct the doubly robust estimator, but I want to achieve the optimality under the PS model. That might be interesting problem. And that problem has been addressed by Kao. So Kao, Kao is I think a student of Chiatis and Davidian. So this Davidian and Chiatis are couple. They are husband and wife. Legal, I mean, true. So and then they are both in the professor, North Carolina State University. So anyway, and his Chiatis is more strong in theory, and Mary Davidian is very good at methodology and application. So they had a good collaboration throughout their professional career. So anyway, okay. So here's the problem. Okay. Now, this is the class of estimator, and now the class is I make it red color, right, on beta hat, beta 1. So that means beta 1 is the parameter that I'm interested in estimating. Then if I for different choice of beta hat, no matter what, they will be unbiased, right? They will be unbiased. But a really interesting question would be, how to obtain the variance? What is the optimal estimator? Well, the problem is actually easy if pi is known. So I think, okay, So this is the original problem, right? So this is a little bit difficult because because of beta hat. I mean pi hat. It is just some pi hat. So okay, let's simplify the problem. And what if first thing is what if I know pi x? Okay, if I know the pi x, then it's actually not difficult, right? Because I can compute the conditional variance, right? If I have this one, then conditional variance will be something like this. Okay, remember, this is the, this guy. If you, so the variance will be like a summation of the variance of ti xi, right? And then pi I, 1 minus pi I and square. Yeah, it's square, something like that. And then variance ti is a pi I times 1 minus pi I. So then you have you get something like this. Okay. So this is a pi I, 1 minus pi I. Oh, sorry, I have a okay. So pi I, 1 minus pi I divided by pi I square is this one, right? And then, so the problem is, so best estimate of beta hat, right? Beta 1 will be minimize this guy. But you don't observe yi for, right? You don't observe yi. I mean, this is actually not really true. We want to, right? This is actually a mean of 1. So so this is actually the y1i, right? Okay. So then basically you want to use Hooke-Thomson type idea. So basically, what's the conclusion? Well, you can solve the weighted least square method, essentially, right? You can use this one as a weight, apply to weight, and solve it. Then you can get optimal estimator under the PS model. Okay. But all this theory is applicable only when this is known. Okay. Now, unknown case, okay, we need to do some extra work. The extra work is, okay, you suppose I have a model, right? So if I have a model, and then maybe I can build a logistic regression model. So here's a logistic regression model. And then for the logistic regression model, I can easily compute the score function, right? Score equation. Nowadays, you can ask ChatGPT to find out this. So I think this is kind of now. You don't have to derive. So this is known. Scope function is just this form. And then you can express it as a kind of calibration form by redefining the, right? So defining H. So then basically your score equation can be viewed as a calibration type equation using H function. Okay. Then what? Then here's a key result. Key result is that basically this is a estimated, right? You have a plugin, plugin, but this guy turns out to be serving augmented regression, okay, with augmented by this HX, which is defined here. Okay, and then here the minimizer. So originally the minimizer, right? The optimal one is so this is the original problem. So, yeah, so the art of problem solving is to translate the original problem into the problem that you can solve, basically, right? You always, so once you translate your original problem into the problem that you can solve, then basically you can find out the answer, right? Because this one, I know how to prove it.
right? Because using the same
technique, because this is a known case. So in the known case, I can easily, say that this is
a way to go. And then the only critical component
is to show this one, right? To show relationship. And I do have a proof. I do have a proof sketched. Okay, so I will briefly. Okay, so this is the original problem.
this is the original problem. And then we want to, remove the dependency on phi hat, right? So we want to do
Taylor expansion. So if you do Taylor expansion, it's a tricky because you're kind of so your coefficient, the function is a function of a beta. So but you can do it
in the closed form.
And then once you obtain that, then you can now you can rewrite. So this is original problem. Then you just did the Taylor expansion, and then this guy is indeed this form. So after that, now you want to solve this, right? You want to solve the minimizer, which has a here and here, and then if you solve it, you get this one. But because of the definition of gamma zero is here. We are lucky in the sense that these two equation. So this is actually a kind of a normal equation. This normal equation turns out to be the same as solving a joint minimization. So that's basically the idea. So I think that's all for today. You can take a look if you're more curious, or you can read the paper. I think the paper is a little bit more difficult to understand, so I did my own way of explanation. But anyway, that's all, and we'll continue lecture this Thursday.